Hello everyone, my name is Mochi Liao. Today I'm going to be talking about a high-resolution precipitation dataset for extreme precipitation events and historical flood event in the Appalachian Mountains in the United States. Here's a little bit of background information about natural hazard-related death in the United States. And what we see is about 18% of the death is related to severe weather, and 14% is related to flooding. On the right-hand side, what we see is a few pictures from the Hurricane Helene in late September 2024. And the situation is even worse for mountainous terrain because in the mountains we don't have enough estimation method, we don't have enough measurement systems. So therefore, in the mountains, estimating precipitation has always been a challenge. So the scientific challenging of estimating precipitation in the mountains involves several parts. So first, we don't have enough rain gauges because it's hard to access to the mountains. And second, in terms of ground-based radars, due to the topographic constraints, the radar beam signal always tend to overshoot and cause large errors in rainfall estimation, and particularly over the valleys. And this region is what we all commonly refer to as the radar blind zone. And in terms of satellites, the satellite data is often associated with coarser resolution and impacted by ground clutter effect and non-uniform beam fielding due to sampling issues, etc. So precipitation estimation in the mountains is characterized by a high spatial and temporal uncertainties in general, and those uncertainties are often depend on scales. So in 2022, we developed a framework that allows us to link the precipitation uncertainty to runoff uncertainty using the water budget closure at flash flood event scales. So basically at these very small time scales, we're assuming that the evapotranspiration and the changes in storage are minimum. And then the idea is the following, that we can, this allows us basically to connect precipitation and the stream flow physically. And this allows us to backtrack the water difference, for example, the water difference between the simulated and observe the stream flow backwards to where the precipitation comes from and apply corrections to the precipitation both in space and time. So for these purposes, we chose 30 basins across the entire Appalachians for 200 extreme precipitation events from 2008 to 2024, 15 years. And the model simulation scale is 250 meter, 5-minute resolution. And then this is a movie showing the backtracking of water difference from hydrograph to the precipitation fields. And this technology or this technique is called inverse rainfall correction, which is published in 2022. And we're applying the IRC or the inverse rainfall correction to the high flows of a flood hydrograph. Essentially, we're assuming the precipitation uncertainty controls the uncertainty, the hydrological uncertainty during the high flows. Typically, for a flood hydrograph, we have the base flow regime, and then early rising limb, and then the rapid rising limb, and then the fast recession and inflection point of the recession curve, and then the slow recession. So we're applying the IRC to these high flow windows, and obviously this framework is done iteratively until the hydrological equilibrium is reached. For example, we're showing here iterations of an IRC example for this event. This event is an event produced by Hurricane Nate in the 2017. And this basin 5 is Catalooch Creek Basin, which is a mountainous basin in the western North Carolina. and we see that the original simulation has very bad KG values, and after 3 iterations it reached to over 0.85, and after 5 iterations it reached to 0.95. And here is the evolution of the KG values from first iteration to the 5th iteration. And we see very significant improvement in the hydrograph. And also in this process, what we found is that the soil moisture, especially the initial soil moisture, that will have some impact on the generation and the propagation of flash floods. For example, the IRC here, for the IRC stream flow, we see that it still has a large discrepancy against the observations due to the uncertainty in the initial soil moisture. So we are introducing a initial condition correction, or ICC, and we incorporated the ICC into the overall IRC framework. And this allows us to address the impact of initial condition. And specifically, we're using initial condition correction ICC for these 2 segments, which is the very early segment delta S1 and the very late segment delta S2. We're assuming that the initial soil moisture play a major role in the beginning of the event, and that is before the rising points of simulation and observations. So we delineate this so-called impact area, and this impact area is calculated based on travel time distributions, and basically initial soil moisture in this impact area will impact the magnitude of delta S1. So the goal is to minimize delta S1, and similarly, we're assuming that the soil moisture near the boundary of the basin can impact the travel time distributions after the inflection point. So those are very long travel time distributions, and therefore we're applying these 2 types of initial condition corrections to the hydrograph. And what we see is that we see overall improvements, very significant improvement to the hydrograph. Here we're comparing the original simulation using the original stage 4, and then we have the blue curve, which is the IRC only, and then we have the coupled IRC ICC results in pink. What we see here is that we see gradually improvements from original rainfall to IRC only, and then the IRC ICC, and then the contrast is substantial, right? For example, for these events, where we see the 2008 February event and then 2011 December event on the bottom right, where we see that the early rise name is being fixed really well by the extra ICC correction. And in terms of the spatial maps of the rainfall itself, let's see the changes in the rainfall. We are plotting the event total rainfall in millimeter. So each column represents 1 rainfall event. So we have 3 different rainfall events. The first row is the original rainfall field. The second row is the IRC only rainfall field, and then third row is IRC ICC. What we see is this overall boxy pattern in the original rainfall field. This is not surprising because this is related to the resolution issue, which is commonly seen in the radar QP dataset due to coarse resolution. And what we see very interesting here is the IRC and ICC. What we see is these precipitation features that are aligning with the topography, the ridges here, and then the valleys. The valleys are characterized with lower precipitation, and then the ridges are characterized with very high precipitation. And in general, what the difference though between the IRC and ICC is that the basin outlet is in the northeast corner here, what we see is that the outlet for IRC is we see this very dark blue regions. This is related to very short travel time distributions. So this is an artifact of the IRC a framework, and if we incorporate that ICC, the initial condition correction, we see reduced uncertainties for very short travel time distributions, and we see improved precipitation structure and also flood simulation, as we just previously explained. Now we're actually comparing the precipitation values against rain gauge networks. Here I'm just showing a partial map of the rain gauge network in the southern Appalachian Mountains, and we're comparing basically the original CH4 and the IRC products. The IRC is fundamentally scale independent because it's based on water budget closure. The water budget closure is a fundamental physics at a watershed scale, so it's not dependent on the scales or the resolution of the models, etc. So we're comparing 250 meter and 84 meter IRC results, and we see overall very good agreement against the rain gauge values in black dots for this region. So the question is, what about using other precipitation data except stage 4? And what about apply this framework to other regions, perhaps bigger sample sizes, etc.? So we use the same framework and apply it to the ERA5 data, and specifically the land component precipitation data over the Alps. The Alps has the densest rain gauge network in the world's mountains, and we chose about 200 mountainous basins in this region, and with over 4,000 events from 1973 to 2024. These are all extreme flood events, and then the model simulation resolution is 900 meter an hourly resolution. We didn't do this for 250 meter because of computational constraints, but what we see here is that the ERA5L is underestimating, is below the 1-to-1 line for most of the rainfall events here. The APGD is a reference here on the x-axis. APGD is a rain gauge only graded QPE dataset using about 8,000 rain gauges in this region. So we use APGD data for reference purposes. And what we see that ERA5L is underestimating, and then ERA5L IRC is improving the precipitation for a lot of the events. Each dot represents one event, and for some extreme events, we see an improvement of 100 millimeter, sometimes 200 millimeter at rain gauge locations. And we compare the CDF, the cumulative distribution function of the event total rainfall, and what we see is ERA5L IRC is very close to the APGD data compared to the original ERA5L. Next, we're looking at the characteristics of this precipitation. So before the IRC versus after IRC. So the first column, this panel A is the original QPE here, showing the strong dependence on elevation. This is not surprising because of this orographic enhancement here over elevation of 900 meter to about 2,000 meter. And what we see, delta QPE is calculated using IRC rainfall and original rainfall, and it specifically is IRC rainfall minus original rainfall divided by original rainfall. So it is a ratio. So here, for example, the percentage is 0.5 or even 1. This means about 50% of underestimation error for a lot of events here at these elevation bands. So basically ERA5L is not able to capture the orographic enhancement happening at very small scales for these elevation bands. And we're applying the ERV5 and ERV5L IRC for hydrological simulation, and we see that the KGG values are dramatically improved when we use the IRC version of data. And we plotted this conditional on the rain rate and also the entire cumulative distribution function. We see that the IRC is dramatically better than ERA5L in terms of the hydrological performances, and also in terms of the comparison against rain gauges previously in the previous slides. So now the summary of this talk is that we developed this water precipitation uncertainty correction approach, a framework that is independent of scales, that is based on fundamental watershed physics, called inverse rainfall correction, or IRC. This allows us to basically reconstruct precipitation estimation for nearly all types of radar QP datasets, and also we introduced this land surface condition parameterization, basically to improve the travel time distribution due to uncertainty in the initial conditions, and this is called the initial condition correction, the ICC, which is also published in 2025. In terms of future work, we're working on the general application of IRC in mountainous basins worldwide. Actually, this work is currently under review, and we're going to apply the IRC for precipitation forecast, aiming to improve flood forecast in the mountains worldwide. And finally, my thanks are given to the funding sources here, the NASA Precipitation Measurement Missions and the NASA Earth and Space Science Fellowship during my PhD there. Thank you. Questions are welcome.